after we have built the KD tree, how we actually search for the nearest neighbor for a new data point. In other words, how we use the tree, right? So imagine we have the same KD tree we built previously, and then we want to find the nearest neighbor of the data point 6,7, right? Which is located here. Okay, so let's use the tree. We're gonna follow this example before seeing the algorithm, right? So the first thing is we set our best distance as infinity, right? Because it's just initialization, and then we set our current best node as known. So in this variable current best, we are going to save our current nearest neighbor. Okay, so the data point 6,7 starts in the root, and we need to calculate the distance between our point and the root. In this case, it's calculated here. Let's just use Euclidean distance, and it's 5.09. So of course we are setting now our best distance so far as 5.09, and our current best data point as the root, because it's the first thing we have, right? We didn't have any data point before. So after we update this, now we need to decide in what direction we will move down of the tree. Shall we go to the left side of the tree, or shall we go exploring to the right side of the tree? So we can see here that the left and the right have associated also the left and the right side of the plane. And how we decide this? It turns out it's very easy. We just need to choose the side in where our query is located. In this case, our query is on the left side of this cut produced by the root, right? On the left side of the 7. How we can check that in the code is very easy, right? Because you just need to see if the x component of the root, in this case 7, is greater or smaller than the x component of the query data point. Okay, so in the right side, it's not going to be our best decision because the query data point is not located in the right side. Why we need to choose this? Because if we go naively and choose randomly the side, every time we fall into the side where our query is not located, it is very likely that we are going to waste computational time, because there is higher probability that the areas in where our query point is not located are going to be discarded or pruned out of our binary tree. So this decision is a key, right? We need to choose first the path in where our query it is located. Okay, so we are going to choose the left side of the tree. And again, we need to calculate the distance now between our data point and the current node in the tree, in this case 5,4. The distance is 3.16, and turns out it is better than our best distance. So we need to update. Our best distance now is 3.16, and our best data point or current neighbor is 5,4. Again, we need to decide if we go to the right side, in this case the upper side of this cut produced by the point 5,4, or to the left side of the tree, which corresponds to the downside of our cut produced by the point 5,4. Again, the way to decide this is choose the side in where our query data point is located. In this case, it is located in the upper side of the cut, so we need to choose the right side of the tree to explore. So we continue, and now we need to calculate the distance between our query data point and 4,7, and the distance is 2. So after we compute the distance, again we compare, and we realize that 2 is smaller than 3.16, so we update our best distance to 2 and our current best data point to 4,7. Okay, now this part is very important. We need to make the question, shall we explore the bad side of the tree? And in order to decide that, we need to figure out if there is any possibility that we could find a point in this area that is better than our current best point. To do that, we just need to draw a vertical line to the limit of this area, because this actually is the best possible data point we could find in this area. Don't forget that the computer doesn't know this draw, right? This picture. So the computer blindly needs to go and make calculations in order to make the decisions. In this case, if we find that our potential point that could be located here could have a better distance compared with our current best distance, then we will have to explore that area. But in this case, we see that 3 is bigger than 2. It means that even if we take into account the best possible point in this zone, that point wouldn't be better than our current best. So this makes us to say we are not going to travel down the tree in this zone, so we can prune this area and we don't have to compute the distance here. So here we can see now one of the benefits of having a KD tree, because in bigger training sets, when we prune one side of the node, of a given node, we can end up saving a lot of computation time. Okay, so we have to continue. Now we already explored all the left side of the tree. We need to go back to the right side that was the bad side at the beginning of the example. And the question again, shall we explore the right side, which is the bad side of this root node? And again, we need to do the same thing. We need to draw, in this case, a line to the limit of this zone. And let's see what could be the best possible point we could find in this area. Turns out that is a point that is located here. So eventually, if there was a training case right here, the distance to that training point would be 1. And that distance is smaller than our current best distance. So this is why we need to explore this area, okay? So again, recall that in order to decide if we explore one side of the tree or not, we need to see if the best possible distance is still better than our current best. In this case, it's 1, so it means we have to explore, okay? So let's go, and then we need to calculate the distance between our query and 9,6. That distance is 3.16. We compare it with our current best, is worst because it's greater. So it means that we do not update. And we need to go down. We don't have to choose sides here because there is just one side. So we go to that side. We calculate the distance between 6,7 and 8,1. This distance is huge, right? Is this point right here. So the distance is 6.32. We compare it with our current best distance, and of course it's greater. So we don't update our best distance. And we finish the exploration, and our best data point, in other words, our nearest neighbor, is 4,7 with a distance of 2.